This is Federico Ardila from San Francisco State University. We're very happy to have our first AlCoVE speaker here speaking about A Tale of Two Polytopes 1, the bipermutohedron. So take it away.
Okay, let me just start a timer real quick so that I can keep track.
Oh yeah, and I will play a little ding when you have 5 minutes left.
Sounds good.
Okay.
Okay. Well, first of all, let me start again by saying thank you so much to the organizers. You are really teaching the rest of us how to deal with situations like this, and it's amazing to be able to go to an international conference like this and not have to go to some consulate and ask for a visa and get treated like crap. So it's actually really special to be here today and to see people from so many places. So thank you to the organizers for putting this together. So yeah, my talk is called A Tale of Two Polytopes Part 1, the bipermutohedron. It's part 1 of 2 talks, and part 2 will be given by Laura Escobar right after this. Okay, so and what I will be talking about in this first talk is joint work with Graham Denham and Junie He. It's the work that has been going on for about 5-6 years, and I'm going to tell you about a small part of that work. And then the second part, which I just mentioned, is joint work with Laura Escobar, and she will be talking about it afterwards, which is the second polytope. Okay. So this is my plan. My plan is to begin by telling you what is. I want to begin by constructing a fan, which we call the bipermutohedral fan. Then I want to tell you about a polytope called the bipermutohedron. And I will be completely self-contained because I want to basically show you this polytope, and if you like it and find it interesting, or maybe it looks familiar, or you know something about it, I will be very happy to talk to you about this. Part 3, which is I think about the second half of the talk, will be just telling you where these things come from. They come from a larger project with Graham Denham and Junie He on the geometry of matroids. But first, I want to just talk about the fan and the polytope, okay? So to construct a fan, I want to start with using as inspiration the permutohedral fan. Maybe some of you are familiar with this fan. So this is the fan. Usually people do it in Rn. We're going to do it in Rn mod R. It's going to be cut out by the hyperplanes xi equals xj. For I different from j, this should say in n. So you have n variables, and you take the hyperplanes xi equals xj, and you look at the fan that creates. But I want to think about this a little bit differently. I want to think about it as a moduli space, as a parameter space, as a configuration space. And so what I want to do is that I want to think of a point in this space Rn to the r as an n tuple of points. Okay, so that's where the Rn comes in. And the mod R just tells you that you can shift the points left or right. You can translate them by the same constant, okay? So you have these endpoints that are moving around. And so this is just the space R to the n mod R. And to make it a fan, I'm going to stratify it by just cutting off space according to the relative order of the points, okay? So for example, if the points are in this position, then I'm going to put them in a strata given by the order set partition. 3 is the biggest, then 2 and 8 are the next biggest, then 0 and 4 are the next biggest, then 1, then 7, and then 5, 6, 9, okay? And so, I mean, this is the same permutohedral fan or braid arrangement that you're used to, but it's going to be useful to think about it in this way, as a moduli space of n tuples of points in the plane, okay? Sorry, on the line. Okay, so this is the permutohedral fan. And now I wish to define the bipermutohedral fan in an analogous way. And the bipermutohedral fan lives in basically Rn times Rn, except you mod R in each factor, okay? But the way that I'm going to think about this is that the bipermutohedral fan is going to be a moduli space for n tuples of points in R2, okay? So a point in here corresponds to an n tuple of points in R2, where the ith point is given by the ith coordinate here and the ith coordinate here. And we do modulo comma translation because we're modeling out by R in each factor, okay? So a point in here is going to look like this, an n tuple of points. There I have it. And if I translate all these points simultaneously, then that's the same point, okay? That's the same point in the moduli space. And again, I'm going to look at all the configurations of points that are moving around, and then I'm going to cut up the space of all possible configurations. I'm going to stratify it according to the following things. So I want to explain to you why this 6 tuple of points corresponds to this sequence, okay? So what I'm going to do is that first I'm going to draw the lowest supporting diagonal in a minus 45-degree angle. So it looks like this, okay? So this is the lowest supporting diagonal. It goes through points 1 and 5. Then I'm going to project all the other points in the x and y directions like this, okay? And then I'm just going to label these projections according to, for example, P4 has a 4 projection here and a 4 projection here, and I do that with each one of the points, and so I get this set of points on this diagonal labeled according to who they are a shadow of, and that's the combinatorial information that I'm going to keep track of. So I'm going to say, okay, there's 3, 4, then 2, then 0, 3, 5, then 1, then 2, 4, and then 0, and so that's going to be my decomposition, okay? Now, if you think about this a little bit, just to start answering some of the questions that I see on the chat, every condition that I'm saying here is linear. So if you want to see what are the points that determine this bisequence, then those are all linear conditions. And so what you're going to see is that basically the set of n tuples of points in R2 corresponding to this bisequence are just a cone, okay? And so really, that's why I'm calling this a fan. This is a polyhedral fan. It's the composition of this space into cones, okay? So this is the bipermutohedral fan. It's indexed by bisequences, okay? So what is a bisequence? It's something very simple. A bisequence is just a sequence of sets taken from your labels where each number appears once or twice, and some number appears exactly once. So let's think about that. For example, why does the number 4 appear once or twice? Because those are the shadows of P4. So it's either P4 either has 2 shadows if P4 is off the line, or if you look at a point on the line, then it only has 1 shadow, and so it only appears once. Okay. And that's why some number has to appear exactly once, because this line is going through at least one of the points, and so that number is going to appear exactly once. So that's the bipermutohedral fan, and there's many other ways to define it. And if you look at our paper, there's several different descriptions, but I like to think of it as a moduli space of points, of n tuples of points, stratified according to their bisequence. Okay. So that's the fan. That's the first thing. And now to tell you about the polytope, well, first let me show you a picture of the fan, and this is the only one that I can draw because the fan is 2n dimensional. So it's 2n minus 2 dimensional, and so this is the only one that I'm able to draw. And if you stare at this picture, you can see these are all the bisequences of 1 and 2, and if you stare at it, you'll see what the inclusion relations are. It's just like in ordered set partitions. They're ordered by adjacent refinement. Okay, and so this is the bipermutohedral fan for n equals 2. And all I want to say right now is that this fan is polytopal. In other words, that there is a polytope whose normal fan is equal to this. Okay. If you want to see the construction, you can look at our paper. The construction is kind of tricky, but the only thing that's relevant to what I'm talking about today is that this polytope exists. One thing that I want to point out is that this is a hyperplane arrangement right here. The bipermutohedral fan for n equals 2 is a hyperplane arrangement, but that's only true for n equals 2. So for n equals 3, n equals 4, this thing is no longer just a bunch of hyperplanes, and so you have to work a lot harder to build this polytope. But the theorem is that there is a polytope whose normal fan is this thing, and so that's the bipermutohedron. Okay. So what is the combinatorial structure of the bipermutohedron? As I just mentioned, the faces of the bipermutohedron correspond to all the possible bisequences. And so this is an example of a bisequence. I'm not able to highlight what I'm trying to highlight, but okay, this is a bisequence. So if you look at the vertices are going to be the finest bisequences, and so these are going to be called the bipermutations. And it's basically a sequence of numbers from 1 up to n, where there is one number that appears exactly once, and the others appear exactly twice. So here the number 2 appears once, and all the others appear twice. Okay, so those are the vertices of this polytope. And they're easy to count. They're given by this number. So this is the number of vertices of this polytope. If you want to know what the facets are, then you want to look at the coarsest possible bisequences. And so they're going to consist of two parts, S and T. They're both non-empty, and their union is the whole set, and not both of them are the whole set. So again, it's easy to count them, and this is the number of facets, okay? And so this gives you what the phase structure is. I'm looking at a question here. So do we think of the number appearing once? Yeah, right. So just to remind you, when we think about this as a configuration of points, how can we understand that there is a number that appears only once? I'm glad that two people asked the same question, so we should definitely address this question. So the number that appears once, remember, comes from thinking of our point configuration. And let me just look at any point configuration. So the way that I started my stratification is by drawing the lowest diagonal that goes through the lowest of these points. In this case, there's two points. In general, there might be just one point. But if I look at the bisequence here, the numbers that appear exactly once are 1 and 5, because those are the lowest diagonal points, okay? And there's always at least one point that's the lowest diagonal, and that's why in all of these bisequences, there's some number that appears exactly once. And that is the reason that both in bipermutations and in bisubsets, there has to be a number that appears only once, okay? I'll say a little bit more about why that line is 45 degrees. I got that question a couple of times. And it is possible to enumerate the F vector of this polytope, but as often happens, the H vector is going to be nicer. And so what I'm going to tell you is what the H vector is, okay? So, okay, so I didn't write this down, but for a polytope, the F vector is the number of faces of each dimension. So the number of vertices, the number of edges, the number of two-dimensional faces, and so on. And there is this nice transformation that takes the F vector and applies a linear transformation and turns it into the H vector, which is the same information, but the numbers sometimes look a little bit nicer. So I'm going to look at the F vector, but in its H manifestation. So this is the H vector. In particular, one thing that is not hard to show is that the bipermutohedron is simple. And in that case, we know that this H vector given by these numbers is symmetric. So that's a nice property of it, okay? So I'm going to call this H vector the polynomial of this H vector, the bi-Eulerian polynomial, because it's the same analogous thing as the Eulerian polynomial for the permutohedron. If you now do this with this bipermutohedron, you get this polytope. The H vector of this polytope, we call it the bi-Eulerian vector or bi-Eulerian polynomial. And so let me just tell you a few things that we know about it. We have a theorem that the H vector is counting the number of bipermutations according to their descents. So if you delete bi, then you get exactly the Eulerian polynomial. So this is an analogous result for the bi-Eulerian polynomial. And I highlight descents because descents are a little tricky. Descents are not quite what you might think if you just think combinatorially. You have to think geometrically. And so if you just look at the polytope and say, okay, you know, what is the polytope one descents to be, then you get some definition of descents, and it's very natural. And you get a theorem like this, okay? Second, the bi-Eulerian polynomial is given by this formula right here. So it's the numerator of this interesting power series where you take all the coefficients something, choose 2, raise them to the nth power. The generating function gives you exactly this bi-Eulerian polynomial. And this is a nice result that actually has to do with Erhard theory. So if you're used to thinking about Erhard theory, then maybe a nice fun exercise for you is to think what's the polytope such that the Erhard polynomial goes here and the Erhard H star polynomial goes here. And this is how we prove this. So this is related to some kind of Erhard theory of a different polytope. Okay. Now, one nice thing about this is that from this expression, you can prove that all roots of the bi-Eulerian polynomial are real and negative. Okay. This is something that's also true of the Eulerian polynomial, and there's some nice proofs. And I had some complicated proof in mind, but I was very happy to go to a beautiful talk by Katarina Johenko, where she, who actually knows how to prove statements like this, showed me that with this expression, it's actually, there's a lot of machinery to prove that polynomials are real rooted, and from this expression, the machinery does it fairly easily. One reason that that's a nice thing is that shows that the H vector of the bipermutohedron is log concave. So the logarithms of these numbers form a concave sequence, which is a nice property that we like in combinatorics, because usually when we have log concave things, there's some interesting deep mathematics underneath. Okay. Okay, so. And I think this is all that I want to tell you about the bipermutohedron. This is the combinatorics, and there's some nice proofs here. But maybe a couple of things that I want to comment. I see a couple of questions about different variants. So why bi? Why not tri? Or why not poly-Eulerian polynomials or things like this? And the answer is basically that all of this comes from geometry. So, I mean, if you like this kind of combinatorics, there's 100 questions that you can ask, and they have nice answers. And I mean, these objects behave nicely. They have nice recurrences. They have like interlacing properties for the roots. They have a lot of properties like this. But I think instead of talking about that, I just want to give you the origin story of where these polytopes come from and why they are defined in this way. Okay. And one thing that I like about this is that it actually comes from log concavity. So, or not only from log concavity, but the origin of this project is related to log concavity. And so this comes from the geometry of matroids. Now, those of you who know me know that I love matroids, and I could talk for a long time about them. But I'm going to try not to do that. Because in some sense, I just want to use matrices as a black box for where this comes from. So matrices are supposed to capture the combinatorial essence of independence. So the idea is if you have a vector configuration like this, then it has an associated matroid, which I have written in this picture, where basically this represents the origin. Right here, this represents the lines spanned by your collection. So the line A, the line B, the line C, and then if you notice the line DE is a single line. These are the planes AB, AC, ADE, BCDE, and this is the three-dimensional space. And so basically you're taking geometric information and encoding it in combinatorial information. And that gives you, you can make a definition that a matroid is a set E, which is supposed to represent the vectors, and a collection F, which is supposed to represent this poset, satisfying some axioms that are not very important right now. Okay, so that's a matroid. A matroid is a picture that looks like this, and it represents. It might come from a geometric configuration like this, or it might not. Okay. Now, as we do in combinatorics, when we have things that are complicated, sometimes we like to encode them, part of their information in numbers. So some important invariants are the number of elements of the matroid. There's 5 elements right here, so that's n equals 5. The rank of the matroid is the height of the poset. In this case, it's equal to 3. The F vector, and I want to be a little bit imprecise here. Please allow me to be imprecise. The F vector is basically given by the coefficients of the characteristic polynomial of this poset. In this case, they look like this. And the H vector is a simple transformation of the F vector, where it's the same information, but the numbers are smaller and sometimes nicer, okay? And the origin of this project comes from these theorems. So I think one of the most exciting recent results in our field by first Ho, then Ho and Katz, and then Adeprecito, Ho and Katz, is that this F vector is a log concave sequence for any matroid, and these were some old conjectures of several researchers. And everything that I'm telling you today comes from a project with Graham Denham and Jun He, where we proved that the H vector of a matroid is also a log concave sequence. This is also some conjectures, older conjectures. And just one quick comment that I want to make is that whenever you have a log concave H vector, you have a log concave F vector. So somehow you know that this second statement is a stronger statement, and so you're going to have to work harder to get it, okay? So we have to work harder, but we're definitely very inspired by this work. And so let me just say a couple of words about how this is proved. At least one perspective on how this is proved. So what Adeprecito, Ho, and Katz do is that they take the matroid, and there's a geometric model of the matroid called the Bergman fan, something that we constructed with Carly Clivens in 2006, where you take this combinatorial information and you actually make it into a polyhedral complex. And this is coming from tropical geometry. This is a tropical model of the matroid, okay? So it's an R-1 dimensional fan, and its support is called the tropical linear space of M, okay? Now, this thing is a polyhedral fan, so it has an associated toric variety, which has an associated Chow ring. And what they do is that they identify two classes in the Chow ring, alpha and beta, such that when you compute alpha to the R-I times beta to the I, you get that this is equal to Fi, okay? Again, I'm being a little bit loose here. Really, what I'm saying is that this is something of degree R in the Chow ring, and because of Poincare duality, the things of degree R are just numbers, and so the number corresponding to this is just the F vector. So the way of thinking about this is that the F vector of the matroid is given an intersection theory interpretation. It's given by the tropical intersection of the classes alpha and beta. And then they have to work quite hard to prove that this fan satisfies the Hodge-Riemann relations, which in particular tell you that a sequence like this is log concave, okay? So this is a very rough idea of how that proof goes. And so I'm just going to take the same thing and just change F for H, okay? So what we do for the H vector is something very similar, but instead of using the Bergman fan, we have to come up with the right fan. And so we have to construct a more complicated fan called the conormal fan, okay? So this is, so to a matroid, we construct something called the conormal fan. And then we have, in principle, the same kind of program where this fan has a Chow ring. We identify classes in the Chow ring such that the H vector of the matroid can be interpreted in terms of the intersection of those classes. And again, we have to prove that this fan is also a Lefschetz fan. In particular, it has the Hodge-Riemann relations, and so this implies that this sequence is log concave. Okay, so it's a very analogous program, and one of the big hurdles is just what's the fan that should go here. Okay, so for the F vector it was the Bergman fan. What is it now for the conormal fan? What does that mean? Okay, and so here you have to take hints from the geometry. And so again, the Bergman fan wasn't pulled out of nowhere. It came from topical geometry, and so we have to think, okay, what's the geometric context that will give us a hint of how to define this conormal fan? Okay, and so there's several geometric hints there. Barchenko constructed critical set varieties that give us hints. There's a construction of Chern, Schwartz, McPherson classes by Felipe Rincon, Lucia Lopez de Medrano, and Christian Shaw that gives us hints. Saba's kind of conormal geometry point of view on CSM classes gives us hints. And so the way that this works is like this. We're trying to construct a fan, and we know from the geometry that the support should be the tropical analog of the conormal bundle, which, if you think about it for a little bit, you realize that it should be the tropical space, the tropical linear space of M times the one of its dual matrix. Okay. Now, you want a simplicial fan because Chow rings of simplicial fans are much more tractable. And so the first thing that you will try is, well, we have a Bergman fan here, we have a Bergman fan here, so why don't you take the product of Bergman fans? That is simplicial, so that looks promising. And there's some geometry here that the classes gamma and delta should be pullbacks of, so gamma should be the pullback of so let me just say briefly what this means. So if I take the product of Bergman fans and I project it to the first coordinate, to the Bergman fan, then a Di-Bracito-Hahn class had a class alpha, which we pull back over here, and that gives us our class gamma, and that can be done. And delta should be the pullback of a class in the Chow ring of this under this sum map here, okay? And geometry predicts that this should all work, and there's some combinatorics that is going to arise here. But the biggest issue is that this map is not a map of fans, okay? The map sigma x of y equals x plus y is not a map of fans, okay? And so let me just wrap up by saying what it has to do with all of this, because is that basically, because we want this to be a map of fans, you need to subdivide this product of Bergman fans further. And then the question is, how are you going to do that? And then the key idea is that for Bergman fans, there was a braid arrangement that did it for all Bergman fans. So if you read my paper with Carly Clivens, and I think the main idea there is take the tropical linear space of M and intersect it with the braid fan, with the permutohedral fan. And so we try to basically do the same thing and say, okay, why don't we take this space and intersect it with a fan that doesn't depend on the matroid, and that should be the bipermutohedral fan. Okay, and so we're basically looking for a bipermutohedral fan that has these properties. There's a natural try, and the first natural thing to try is actually the harmonic fan that Laura is going to be talking about, which is a wonderful fan. It has all the right properties except that it's not simplicial. And so what we need to do is take the harmonic fan that she will tell you a lot more about, and just find what is a nice polytopal simplicial refinement of that harmonic fan. And we have to basically, at this point, it's a little bit more of an art than a science. You have a fan that is very natural, and you have to find a nice simplicial refinement that is polytopal, so that it has it's the normal fan of a polytope. And basically this fan that, when I define it to you, it seems strange to you. This is the nicest fan that we could find that satisfies all the geometric requirements to make this program work. Okay. So if you're interested in more of the details, I'm happy to talk to you, but I think this is a good place to stop. And thank you for your attention.
Great, let's thank Federico. Could he give a clap, or use the clap emoji? Excellent first talk. So we have a couple minutes for questions here. There's some questions rolling in. I wasn't sure if there was some that haven't been answered, but there's some new ones here from Fig Reiner. You can address this. Is there a notion of biposets corresponding to geodesically convex collections of top dimensional cones in the bipermutohedron fan?
Yeah, it's a great question. So in the braid arrangement, you can think of defining a poset by saying that a poset is just a collection of cones that is convex in the braid arrangement, and so you could define a biposet like this, and presumably linear extensions should be the bipermutations, and so on. We haven't looked at that. But it certainly seems like a very plausible thing to define. I mean, you can make the definition, and I guess the question is, what are the properties? And I think that would be very interesting to explore.
Great. Well, thanks, Federico, again. I think in the interest of time, we're going to cut off questions here to get Laura Escobar's talk ready. And so, yeah, thank you very much, Federico. It's a great talk.
Yeah, thank you.